These are the practice problems for the Algebra 1 Mid-Unit 5 test. A bond is initially bought for $250. It doubles in value every decade. Number 1, complete the table. So at 0 decades, this is the time that the bond has bought. And they told us it's worth $250. Then we know that it doubles every decade. So 250 times 2 becomes 500. 500 times 2 becomes 1,000. 1,000 times 2 becomes 2,000. And what we're doing here is we're saying 250 times 2 to the power of d. Number 2. How many decades does it take before the bond is worth more than $10,000? So for number 2, we know that after 3 decades, it's at 2,000. So at 4 decades, it would be 4,000. At 5 decades, it would be 8,000. And finally, at 6 decades, it would be 16,000. So it would take 6 decades. And number 3, write an equation relating V, the value of the bond, to D, the number of decades since the bond was bought. So what we can do is write this in function notation. The name of the function is V. The input is D. And that's going to equal the starting amount, 250, times the growth factor. Doubling means multiply by 2. And that growth factor is to the exponent of the input, which is D for decades. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification before the test. Here are 3 equations defining 3 exponential functions, f, g, and h. F of x equals 100 times 3 to the power of x. G of x equals 100 times 3.5 to the power of x. And h of x equals 100 times 4 to the power of x. Number 1. Which of these functions grows the least quickly? So we're looking at growth, and we want the least quickly, or slowest. What tells us that is the growth factor, the number with the exponent. The smaller the growth factor, the more slowly it grows. The bigger the growth factor, the faster it grows. So for number 1, 3 is the smallest growth factor. So f of x grows the slowest because it has the smallest growth factor. Then they want to know which one grows the most quickly. Again, we're looking at the growth factor, and we want the biggest growth factor. So that means h of x grows the quickest because 4 is the largest growth factor. Number 2. The three given graphs represent f, g, and h. Which graph corresponds to each function? Well, we just said h is growing the fastest because it has the largest growth factor. So that means the blue line A would be h of x. The one in the middle would be g of x because 3.5 is the growth factor in the middle. So B is g of x. And finally, we have C, which is the slowest growing, and that's going to be F because 3 is the smallest growth factor. So C must be f of x. And number 3, why do all three graphs share the same intersection point with the vertical axis? When you are on the vertical axis, your x value is 0. So f of 0 equals 100 times 3 to the power of 0. Anything to the power of 0 is 1, and anything times 1 is itself. So it has an intercept of 100. G of x equals 100 times 3.5 to the power of 0. Again, anything to the power of 0 is 1, and anything times 1 is itself, so it also has a y-intercept of 100. And finally, h of 0 equals 100 times 4 to the power of 0. Again, anything to the power of 0 is 1, and anything times 1 is itself. So you can see if we put 0 in for the exponent, all of the growth factors become 1, and anything times 1 is itself. So all of them have the same intersection point with the vertical axis at y equals 100. If you have any questions about how I solved this practice problem, please use class time to ask for more clarification now before the mid-Unit 5 test. Here is a graph of the function f defined by f of x equals a times b to the power of x. Select all possible values of b. So the first thing to understand is that b is the variable with an exponent. So b is the growth factor. If b is the growth factor, we want to think about what kind of designs different growth factors would create. If b were greater than 1, then we would have exponential growth. That's not what we see here. If b was equal to 1, we would have a straight line from the y-intercept because we would always multiply by 1. It would stay the same. And if b equaled 0, then 0 to any power is 0, and anything times 0 is 0, and we would simply see the x-axis. What we have here is exponential decay. And this happens when b is between 0 and 1. So we want to look through, and if the choice is between 0 and 1, then it is a possible value. We said it couldn't be 0 because that would just be the x-axis. So A is not correct. B is 1/10. That is greater than 0 but less than 1. C is 1/2. That is greater than 0 but less than 1. D is 9/10. That is greater than 0 but less than 1. E is 1, and we said that would just be a horizontal line at the y-intercept. So that can't be correct. F is 1.3. If you were multiplying by 1.3, your numbers would keep getting larger, and we would see exponential growth instead of exponential decay, which is what we have. So it can't be F. And G is a function, but that function is 8 over 5, which is the same thing as 3 and 3/5. That's clearly greater than 1, so G cannot be a correct answer. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification before the mid-Unit 5 test. The value of a home in 2015 was $400,000. Its value has been doubling each decade. If V is the value of the home in dollars, write an equation for V in terms of D, the number of decades since 2015. When we write this, function notation says we have the name, which is V. In parentheses, we have the input, which is D for decades. That equals the starting value, or y-intercept. In this scenario, that's 400,000 times the growth factor. We know it's doubling, so that's the same as multiplying by 2. And the growth factor has an exponent of the input, which we said was d decades. What is v when d equals -1? What does this value mean? So we would have v of -1 equals 400,000 times 2 to the power of -1. The negative exponent means we want the inverse, so this becomes 1/2. And 400,000 times 1/2 is 200,000. So v of -1 equals 200,000, and this value means the value was $200,000 one decade before 2015. And number 3, what is v when d equals -3? What does this value mean? So v of -3 equals 400,000 times 2 to the power of -3. The negative tells us we want the reciprocal, or the inverse, 1 over 2 cubed. 2 cubed is 8, so this becomes times 1 over 8, and that equals $50,000. So what does this value mean? The value was $50,000 3 decades before 2015. If you have any questions about how I solved this practice problem, please use class time to ask for clarification now before the mid-Unit 5 test. A population P of migrating butterflies satisfies the equation P equals 100,000 times 4/5 to the power of W, where W is the number of weeks since they began their migration. Number 1. Complete the table with the population after different numbers of weeks. So, in the beginning, we know that there is 100,000. After 1 week, we multiply 100,000 by 4/5, and that leaves 80,000. After the second week, we multiply by 4/5, And that's 80,000 times 0.8. There's still 64,000 butterflies. Now we multiply by 4/5 again. And that's 51,200 butterflies. And we're going to multiply one last time. 40,960 butterflies. So to fill out the table, simply start with your beginning population after 0 weeks. Then each week multiply the y value times 4/5 to get the next y value until you've filled in the entire table. Number 2, graph the butterfly population. Think carefully about how to choose a scale for the axes. So our input is going to be weeks. And I'm just going to number these by 1. Our output is the population. And I'm going to label this every 20,000. Now we can plot our points. Each column is a point pair. So we have a point at 0, 100,000. That's the y-intercept. Then I have a point at 1, 80,000. Then I have a point at 2, 64,000. Then a point at 3, 51,200. And a point at 4, 40,960. Number 3. What is the vertical intercept of the graph? What does it tell you about the butterfly population? Well, the vertical intercept is the y-intercept, and that is at 0, 100,000. Tells us the starting population was 100,000 butterflies. And then number 4, about when does the butterfly population reach 50,000? So this line right here would be 50,000. We can see that at week 3, we're still just a little bit above it at 51,200. But by week 4, we're way down here at 40,960. So the butterfly population reaches 50,000 just after 3 weeks. If you have any questions about how I solved any of the practice problems on this review worksheet, please use class time now to ask for clarification so that you can be as best prepared for the test on Monday as possible.